So now it's on when I come in. And so we'll do, I typed in most of it. I just want to walk through it. I think that it's good just to have one more example kind of completed that you can refer to, since this is the hardest type of law of sines case to deal with. So we're given an angle and two sides. When you're given the angle and two sides, you know that it's going to be an ASS case if you have that situation right there where you have an A and an A, or a B and a B, or a C and a C. So you've got an angle and the opposite side. So if we were given an angle and two sides and none of the letters matched, then you would know it's SAS. If you're given two sides and an angle and none of the letters match, it's SAS. Two sides in an angle where there's a match, then you know it's going to be the ASS case. All right, so the procedure that we used, which I think works great, is to put an unknown as the base, and then the angle that you know, the only angle that's given, and then the side and the side. If you do it that way, it's, I think, really intuitive to figure out how tall the triangle is, and that gives you insight into whether, in this case, side A will reach the bottom, will reach the base. And when we're using our right triangle trig, we see that the sine of A is h over b. So this that right triangle there we can use to find the h, to find the height, right there. So sine of angle A, opposite over hypotenuse, h over b. Solve for h, plug in our numbers, and we get that the height's 20.4, and we see that that second side is greater than 20.4, and it's less than 24. So that tells us that we have two triangles. So is there any confusion on how we make that assessment, whether there's two triangles or one or zero? Is that logical enough, hopefully? All right, so therefore there are two triangles, and the way we did this last class, we said we'll call one the outer triangle, one the inner triangle, and we'll start with the outer triangle because the only choice is to solve for this angle down here. That's our only choice, is to solve for that angle there, which in this case we would call this angle B. And over here, usually I put stars on these guys. Usually I would call that A star, B star, and then this would be capital B star. So outer triangle, inner triangle, and we label them. And what's the reason that we're going to start with the outer triangle first? Yeah, we can solve the inner from the outer, and we solve the outer first because that angle is acute, right? Acute. So we don't go with this one because it's obtuse. And law of sines, at some point you have to take inverse sine. And when you take inverse sine, you can only get an angle between 0 and 90 if you take inverse sine of a positive number. So we're going to solve for that one first. And let's go for it. So I don't think I wrote it out that far. Yeah. Okay, so law of sines tells us that sine of B, and again, I'll just reiterate that I think that whatever your unknown is, putting it in the top left, I think is the easiest way. It reduces some of the algebra steps later. So sine of B over side opposite will equal, there she is, will equal the known side and angle pair. And so that's going to be the 58 degrees and the 22. And we just have to make sure that we're consistent. So I selected an angle to go in the numerator, so we've got to stick with an angle in the numerator on the right. So angles up top and sides down below. Oh. And I forgot my calculator again, Kelly. So b will equal, we'll multiply both sides by 24, and then we'll take the inverse sine of both sides. So right here, we're taking inverse sine, so we really would love to make sure that that's an acute angle so we don't have to deal with reference angles. And the way we selected it, it is. And when you type that into your calculator, what do you get to the nearest degree for angle B? 68 degrees. All right, so now we have two angles. And once we have two angles, we can use our subtraction property. And the angle that we're missing inside, let's see, that's B, so that one's called C. So angle C will be 180 minus 68 minus 58. If we subtract all that, what do we get? 54 or something? Somebody double check my arithmetic. All right, thank you. So that's angle C. And then the last unknown for this triangle is little c. And so little c we will find by using Law of Sines. So we'll say the side little c, we'll put that in the top left. And then over that is the sine of the angle opposite little c, which is sine of 54. And then we have to put our known ratio, the original known ratio, except we have to flip it from where it is right here, where we use sine 58 over 22. Now we have sides on top, so we're going to do it this way. And then little c is solved for pretty easily. We multiply both sides by sine 54, type all this into the calculator, and let's see what we're going to round to. The other sides were to the nearest unit, so we'll round that side, little c, to the nearest unit also. And what do we get when we type all that in? 91? 21. Okay, that sounds more reasonable. 91. All right. Cool. Any questions on any of the steps there? So there's no one step in this problem that's that complicated, but there is a whole series of things that you need to do and make sure that you're doing them in the right order, so you don't get led astray. So that's the inner triangle. We'll always solve the inner triangle first. Then we'll jump over to the outer triangle. And the angle that we have to solve for first is B star. And B star, we talked about that a couple of times. B star is nothing more than the supplement of B. And we found B to be 68. So B star is going to be, is that 112 degrees? 112 degrees for B star. Any question lingering on why B and B star are supplements? We're using an isosceles triangle property. If that's angle B, then so is that. That's angle B right there. So those two angles are the same, which makes that angle supplementary. So B star is supplementary to B. Then we'll go in the same order here. Now we'll find C star. So C star with the subtraction property. So it looks like 10 degrees. 10 degrees. And then we solve for the side opposite angle C star, which we call little c star. And little c star, put that on top. And then sine of 10 degrees down below. And it will always be the same as the ratio that we used over here with c, with little c. Same ratio over on the right side. 22 divided by sine 58. So little c star will be 22 sine 10 degrees over sine 58 degrees. Got that. Type it into our calculator, round to the nearest unit, and what do we get? 4. Cool. Nice. Can you do that on the test? Yes. You can. Practice it a few times, and you can definitely do it on the test. Okay. Are we ready for 8.3? Complex numbers. Complex numbers. In college algebra, you may or may not have graphed complex numbers. In college algebra, quite frequently you deal with operations of complex numbers, but you might not graph them. And complex numbers are a two-dimensional set of numbers. So that's completely different than the other number systems you've worked with. Right? The real numbers is a one-dimensional set of numbers. When we graph the Cartesian plane, we're taking a set of real numbers and then juxtaposing it with another set of real numbers. So it's two sets of reals. Complex numbers are totally different. In order to see the set of complex numbers, you need two dimensions. So the complex numbers are a two-dimensional set of numbers, which means they have some very different properties. The first property that's totally different is that you cannot say one complex number is bigger than another. Okay, because it's a two-dimensional set. You could say that one is further from the origin than the other, but you can't say one is bigger than the other. With the real numbers, you pick two distinct real numbers, you know one is greater than the other. That's a very fundamental property of the real numbers, that they're ordered, that there's an order to them. Pick two distinct and one's going to be greater than the other. Complex numbers, no order. There are patterns, but there's no order. You can't say one complex number is bigger than another. Okay. So we picture the complex numbers with the complex plane, and we'll label the complex plane with a big C and a line through it like that. And that's in contrast to, we use this symbol R for the real numbers. And we use this symbol R squared, which we usually just say R2. We don't, it doesn't really mean to square it, but we call it R2. That's the Cartesian plane if it's real and real. And then we use the C for the complex numbers. And the horizontal axis we call the real axis. The imaginary axis is the vertical axis. And the number 4 minus I means go 4 in the real direction and down 1 in the I direction. So that is the number 4 minus I. So it's a two-dimensional set of numbers, and we treat it almost like an ordered pair. Very similar to an ordered pair. The number 6 plus 3i, we go over 6 in the real direction, we go up 3 in the I direction. That's that number right there. That's 6 plus 3i. Number 7, the number 3, that's 3 plus 0i, so that's a real number. That's right there on the x-axis, the horizontal axis, the real axis. And then minus 2i is down here. Okay? So that's what they look like. It's a two-dimensional set of numbers, and then we have to figure out what kind of properties they have. Okay. Oops. So first property we talk about is the absolute value of a complex number. A lot of books will call it the magnitude of the complex number. This book calls it the absolute value. It means the same thing. So the absolute value of a complex number is its distance to the origin. And that's a pretty consistent interpretation of absolute value. When we're talking about absolute value of a real number, you should be thinking of distance to the origin. Absolute value of -3 is 3 because -3 is 3 from the origin. Same idea here. absolute value of a complex number is going to be its distance to the origin. And when we find distance to the origin, we're just thinking Pythagorean theorem. We're thinking of radial distance the way we've been doing all semester. So what, well, that's a bad color. So what about that number right there? What would be the magnitude of minus 2i? How far from the origin is that? 2. Magnitude of 3. How far from the origin is that? 3. Magnitude of 4 minus I. How far from the origin is that right there? When we talk about this distance to the origin, here we really are just interpreting it like a Cartesian plane and like that's an ordered pair 4 comma minus 1. So that's what this is, right? That's just the Pythagorean theorem, square root of the sum of the squares. And so the distance this number is from the origin is going to be the square root, the square root of the sum of the squares. So square root of, we square the 4 and get 16, and we square the negative 1 and get 1. So we think of the coefficient of I as negative 1, so that's what we're going to do for the squaring. We're not dealing with the I. We're just taking the coefficient. So the formula says take the number in front of I and put it right there and square it. So we ignore the I when we're finding this distance to the origin or this magnitude thing. And then 6 plus 3i, the magnitude of that. Square, oh, and I didn't finish this off. Square root of 17 is that distance. Can't simplify that. Distance here would be 36 plus 9. That's the square root of 45. That can be simplified. That's 9 times 5. So that'd be 3 root 5. So that would be the distance to the origin for that. Okay, so nothing crazy so far. Really just using ideas that we've already been using most of the semester. Radial distance. Okay. Now, before we go there, I want to say one more thing about the properties of the complex numbers. So the I is the piece that tends to be the mysterious piece, and the definition of I is that I is the number such that I squared is equal to negative 1. So that's just the definition. That's how we are going to define what I is. So I is you can think of I as the square root of negative 1 if you want. Usually we use this square property, but you absolutely can say I is the square root of negative 1. So in math, we start from definitions, and then we prove things, or we make conclusions, we solve problems, but we tend to start with the definition. And we come up with these definitions based on stuff that works, some sort of empirical evidence for why that would be a good definition. Like a parabola. If you think about a parabola has a very concrete definition, which you learned in college algebra. You know, at first when you studied parabolas, you were just told, if you graph a quadratic, the graph will be a parabola. The shape is called a parabola. But in college algebra, you didn't define a parabola until you went into the conic section part. You know, when you're given a quadratic equation, x squared plus 2, you picture the quadratic graph, and we call that graph a parabola. But we didn't talk about the properties of that parabola until you get to conics. And when you get to conics, you learn, oh, there's a directrix, there's a focus, and a parabola really is the set of points that's sort of sandwiched between the focus and the directrix. There was a very formal definition. So the same idea is, and then you can figure stuff out from that definition. The same idea here is that we're coming up with this definition, and we're doing it because it works, because there is all sorts of applications that we can solve with this definition. If this definition didn't lead us to solving a bunch of problems, it'd be worthless. And that's what we do in math. We come up with a definition that's going to lead us down a road where we can solve a bunch of problems. And I think it's really helpful to realize that that it's just a definition, even though you can't sort of picture the square root of -1. That's fine. There's all sorts of things you can't picture, and we use the results just fine in everyday life. And so knowing that there's lots of applications that use I is super important. And I think did I release something? I had a news item about complex numbers. I don't know if I released it yet. I'll take a look and make sure I release it. It's a good article on applications using I, essentially. Let's go to a new slide for a minute, and let me draw a complex plane here. And I want to just make a couple of simple observations. So if this is the real axis here, this is the imaginary axis up here. Let's just notice this. What number is that? 2. Now, if we multiply that number by I, we end up here, 2I. And using the definition of I, if we multiply that by I, we would get 2I squared, which is going to be 2 times -1, which will be -2. That is over here. You agree? -2. And if you multiply that by I, you would end up right here. And one good way to think about multiplication by I is that multiplication by I leads to a 90-degree rotation. And that direction would be counterclockwise. So that's you can think of all sorts of things in nature where a rotation is super important. And one of the primary applications of complex numbers has to do with electricity. And if you ever start to study, depending on what field you're going into, electricity and magnetism, a bazillion applications that involve I. We can model electricity. The electricity that comes into buildings uses alternating current. And the combination of trig functions and the imaginary, they call it the imaginary unit, I, the combination of those allow you to build equations that model electricity's movement exactly. Same thing with magnetism. Magnetism has all sorts of crazy properties, and you can model those properties with I really easily. Now, back in the day when they came up with this definition, I squared equals -1, they called it imaginary, because it was a very abstract mathematical thing at the time, and there was not a concept of all the applications that it would be used for. So using the word imaginary is a bad name for this, because it makes you sort of think like it's super mysterious, and it's not that mysterious. The formal definition, and that's how it happens in math all the time, where mathematicians come up with something, and people that aren't mathematicians think, that's stupid. Why would you do that? Why would you use that definition? Another good example is you guys are all familiar with Euclidean geometry, where you assume parallel lines never meet, right? That's standard Euclidean geometry. So then there's two other types of geometry, elliptic geometry and hyperbolic geometry. And you can assume that parallel lines meet at one point called infinity. And at the time, folks are thinking, well, that's the stupidest thing I ever heard of. Well, then they start to find applications, and you all know that gravity can bend space. And so then Albert Einstein ended up using this type of geometry. It's called Riemannian geometry, is kind of the general name for it. That's how he proved his general theory of relativity. Without that geometry, he never would have been able to do that. And so that's how it happens in math all the time. They sort of come up with some crazy idea, and it seems totally crazy. Fractals is another example. It wasn't until the 70s where the science of fractals really took off, and it just seemed like some stupid idea to talk about a partial dimension. And then in the 70s, they really explored that a lot. So in math, it happens all the time. They come up with an abstract definition, and then years, decades later, oh, wow, there's actually an application for that. So this is one of the first ones. And often some of the terminology that gets utilized when these definitions are starting tends to be, in the long run, probably not the most appropriate terminology because it makes it seem like something it isn't. All right, so let's talk about the connection then between complex numbers and trigonometry. There's an obvious connection because we are graphing these complex numbers in a plane, and you clearly see there's an angle. And so what we're going to do is convert our complex numbers. This is the standard complex form, a plus bi form. So these complex numbers all have this form, a plus bi. And what we're going to do is convert that to a trigonometric form where we identify the angle of rotation counterclockwise, and we identify the distance to the origin. And so this is going to give us another way to think about complex numbers. We're going to rewrite our complex numbers a plus bi as r times cosine theta plus I sine theta. We will use an abbreviation for this, or I will. The book doesn't like to do this. Most books do it, but this book doesn't. You can abbreviate that. Instead of writing cosine theta, sine theta every single time, you can write CIS theta. Okay, so let's figure out why that is what it is. So right triangle trig, if you take the cosine of theta, you get a over r. If you take the sine of theta, you get b over r. Solve the top equation for a, solve the bottom one for b. And another way to think about a then is that it's r cosine theta. Another way to think about b, the vertical distance, is r sine theta. So that's going to be the trig right there. This piece here, that's going to put us on the complex unit circle. And then this piece tells us how far from the origin. So if we're dealing with an r value of 1, we're staying on the complex unit circle. If that r value is 2, we're going to move to 2 units away from the origin. If that were 1/2, we'd move inside the complex unit circle to 1/2 a unit away from the origin. So that right there, that r is distance to the origin. Distance to the origin. So r CIS theta, r times the quantity cosine theta plus I sine theta, those two are always the same. It's always theta. It's not theta 1 and theta 2. It's theta and theta. Those match. Those angles are always the same. All right, so we have to figure out the trigonometric notation for these guys here. And let's go ahead and start with, let's start with 18, just to start with one that's a little bit easier. So the notation says that we need r and we need theta. If you know r and you know theta, you know the complex form or you know the trigonometric form of the complex number. What is r for this case? How far away from the origin is 4? 4. So r is 4. And what would be the angle? So you're imagining 4. You're imagining this plane right here, and you're out here at 4, right there. So what's the angle if you're going to rotate from the positive x direction, positive x-axis? 0. So theta is 0. So that allows you to write this complex number then. That's number 18. So 4, that's the standard algebraic form. Trig form is going to be r, that's 4, times cosine theta plus I sine theta. Let me move this stuff over a little bit. Put you over there. So 4 parentheses cosine of 0 degrees plus I sine of 0 degrees, or 0 radians. Let's go with radians. Just kind of depends on the problem. Doesn't really matter. So that's the trigonometric form. You could shorthand this as 4 CIS 0. So that's the trigonometric form. And there are great applications for this trigonometric form that will make some work a lot easier. Let's go with another easy one first, before we get to some of the more complex ones. Let's look at 20. How far from the origin is 20? 7.5. And what would theta be in radians there? So 7.5i. That's straight up, right, in the vertical axis? So 90 degrees, 5/2 radians. Yep. So the trigonometric form for 20 then, we would say that 7.5 is the same as 7.5 times cosine pi/2 plus I sine pi/2. And notice that we put the I in front of sine so that it doesn't somehow mistakenly get pulled into the angle. You could put a multiplication symbol and an I on the tail if you wanted, but for this, most of us will put the I right in front of sine. And you can see why the shorthand notation is convenient, because you're writing cosine and sine every single time. You're writing pi/2 twice every single time. So that abbreviation is very convenient. All right, now we have to do some more complicated ones. Let's see what I want to put another slide up. Let's do that. And let's grab 14 and 16 and 22. Let's grab those other ones and use those. So 14 and 16. Let's move you to the next page. Okay. So there are two ways to get at these. It could be that these are nice numbers that are on the complex unit circle that are scaled off of the complex unit circle from terminal points that we know, like root 3/2, 1/2, or something like that. So that would allow us to come up with the trigonometric form in a geometric way. Another way is just to purely do it algebraically. And I'll do both of these in both ways just so you can see kind of the difference. So with 14, let's just do it purely algebraically. First, let's identify that A is minus 10 root 3, B is positive 10. So if we're trying to find R, we don't need to think geometry at all if we want. We can just say R squared is A squared plus B squared. So R squared is going to be, when we square that, we're going to have 100 times 3, so that's 300, plus 100. And then R will equal the square root of 400, which is 20. And it's always positive, just like we've always done this semester. R is a positive number representing distance from the origin. And, yeah?
So when we square that B or whatever,
Yep.
Should we bring the I down with that?
Nope.
No?
I is not part of B. So the complex numbers are A plus B times I. So for that distance, we only use the B. The I is not part of the distance, so we're going to exclude the I. Just look at the coefficient. How about the angle? So first off, we certainly want to identify what quadrant we're in, just to make sure we're, not coming up with the wrong sign, S-I-G-N. Okay, so that's in quadrant 2. Everyone agree? All right, so quadrant 2. Usually what folks will do if they're trying to find theta, they will identify the tangent function. You absolutely could do another trig function. If you drew a picture, you could find the radial distance. We already did, so we could use another trig function. Most people with complex numbers are just going to say tangent is b over a. y over x, and go from there. Now, inverse tangent gives you an angle on the right side of the circle, not an angle in quadrant 2, so we would have to use a reference angle. And the reference angle is the inverse trig function of the absolute value of the right-hand side. So we can find that absolute value, that the tens will cancel, and we're going to end up with 1 over root 3, which if we rationalize would be root 3 over 3. And we know that, right? Root 3 over 3, that's the less steep. So if we type this into our calculator into degrees, it would give us a nice number. But if we type it in radians, it's going to be a little messy. So what would the radian angle for that be? Pi over 6. Yep, pi over 6. It's the less steep one, pi over 6. So now that would allow us to conclude that in quadrant 2, we would have to subtract pi over 6 from pi, giving us 5 pi over 6. And now this number up here, we also could have gone straight for it, but I want to make sure you're clear on how you would do it with a reference angle, because if this number is not a special ratio, we have to use a calculator to get through that process. We have to use a reference angle to get through that process. So there is our theta. So now we have our r, we have our theta. That allows us to conclude that this number up here is r times the quantity cosine 5 pi over 6 plus I sine of 5 pi over 6. And again, that's a pain in the neck to write all that stuff out. It's a lot quicker to write. Oh, that corner of the board does not like the pen. So 2 CIS 5 pi over 6. Nice, concise way. Oh, 20. Yeah, that's a 2 with a 0. 20. Thank you. 20. Thank you. All right. And let's do 6. Oh, before we do 16, let's do this one totally geometrically then. So, and this is a way I love to do it geometrically, of course. So we're in, actually, let me do it via a circle. Let's not take you. Let's get a circle up here. And what do you think I should choose? Based on the numbers that we see, are we thinking, yeah, 8 or 12? We see the root 3, so we should be saying to ourselves, if the ratio is nice, it should have something to do with a 12-sector circle. So let's go with a 12. And here's what we'll do. So it's minus 10 root 3 plus 10. When we look at this unit circle, we know these two terminal points. If I wrote them as terminal points in the complex plane, that first one, this one up here, would be minus 1/2 plus root 3 over 2I. So that's in the complex plane, that terminal point. This one over here, do this one in red, would be minus root 3 over 2 plus 1/2 I. So those are the terminal points in the complex plane. And what we would be doing if we're doing this geometrically, we'd be saying to ourselves, all right, first off, would I be at the 5 pi over 6 mark, or would I be at the 2 pi over 3 mark? Or I said those wrong. Yeah, no, I didn't. 2 pi over 3 or 5 pi over 6. We have to figure out which one do we think we would be at. When we look here, we see the root 3 is with the first coordinate, the x coordinate right there. So our guess is that when we look at these two numbers, oh, if it's a multiple of one of these numbers, it's a multiple of this one because the root 3 is in the first position. Right? That's what our guess would be. So then we're imagining, okay, that complex number is if it's outside of the unit circle, which we know it's going to be 20. It's outside of the unit circle. It's somewhere over here. If the radius was less than 1, it would be on the inside. But we're out here somewhere. And our question is this. Okay, we've got minus 10 root 3 plus 10i, is that what it was? Plus 10i. The question is that a multiple? Is there some constant that, we'll call it r, mysteriously, that we can multiply the complex number that we know on the unit circle by to get the number in question? And when we look at that, it's pretty obvious, I think, what r has to be. If you look at the second position in particular, it's probably super easy. You're saying r times 1/2 is 10. So r has to be 20, right? 20 times 1/2 is 10. And then you double check your first number. 20 times this. 2 goes into 20 10 times. 10 times negative root 3 is right there. So that would be a geometric way to do this. So this would imply that r is 20. And then we're making the same conclusion that the complex number, we need a name for this complex number. Usually we use z's to represent complex numbers. I don't know why this book doesn't like to label their complex numbers with a name. I'm going to call it z. So then that complex number z we could write as 20 cis, and we see our angle right there is 5 pi over 6. So that's the geometric way to look at it. Sometimes a combination of the two is helpful. We'll probably see that with the next one. So any questions on any of the steps there? We'll do a few of these so you kind of get that sense of the way I would refer to this process is that we are scaling a terminal point on the complex unit circle. We're taking a terminal point on the unit circle in the complex plane and then scaling it. We're either moving it away from the radius of 1 or we're moving it closer to the origin. We're either stretching it or compressing it. All right, let's take a look at the other one, minus 5 plus 5i. That one's a little bit shorter. And I just said it, but I still have to look again. Okay, it's minus 5. Are we in quadrant 2 again? All right, so let's take a look at that one. This one, a couple of things you can do. I think that whenever you can, drawing a picture of some sort is just helpful. And we know that this is bisecting quadrant 2. So I'm thinking of that complex number right there. And that should allow us to identify the angle and the radius pretty darn quickly. When we're looking at the point, we kind of see, oh yeah, the angle is 3 pi over 4, right? Theta is 3 pi over 4, and r is the square root of the sum of the squares, so we're going to get square root of 25 plus 25, which is going to be square root of 50, which is 5 root 2. So from that picture, you can really see pretty quickly what the angle is and gives you a good sense of what the radius is. So this complex number, we're going to call it z. It's nice to give it a name. Z will be 5 root 2 multiplied by, and I'll just write the shorthand this time, CIS of 3 pi over 4. If we were doing it the geometric way, what unit circle do you think we would pick, 8 or 12? We're going to pick an 8. We're picking an 8 because we're thinking of it as bisecting quadrant 2, and the 8 sector is the unit circle that has bisectors. And we would be saying, oh, it's probably a multiple of this point right here. This terminal point is minus root 2 over 2 plus root 2 over 2i in the complex plane. So that's our terminal point in quadrant 2 for the 8 sector unit circle in the complex plane. And then we are saying to ourselves, all right, so this number minus 5 plus 5i, that's equal. Is it a scalar multiple of that? Is there an r that I can multiply that point by to get the negative 5 plus 5i? And the answer is yeah, sure. if we multiply this number by 5 root 2, we're going to get minus 5 here. You're going to see that? So if you're not sure how to, if it's not obvious, like the last one was pretty obvious, so we're basically trying to solve this equation. So if we just look at the first position. If you solve either, you can do the first position or the second position, doesn't matter. It's going to give you the same number. So if you're solving that for r, it turns into a plus. You get 10 divided by root 2 equals r. You rationalize the denominator, and you get the same r value that we got over here. So r is going to be 5 root 2. And then you would conclude that your complex number z is equal to 5 root 2, CIS 3 pi over 4. Sometimes a combination of visual and the plug and chug method work, but they certainly complement each other. All right, you ready to try one? Oh yeah! Look at that enthusiasm. First we have to go backwards. Sorry. We'll go backwards first. So, given the trig form, now I want you to try one. Gotta try one. Gotta try one. All right. So, well, the iron is hot. All right. So take this one and see what you can do. So let's suppose we have 2 root 2 minus 2 root 2i. So that's a complex number. Let's call it z. And see if you can figure that one out. So find the trig form of that complex number. Put another one up here too for the speedies. Let's go through the first one here. So if we're thinking about a unit circle, I think that the 8-sector unit circle is pretty obvious. We see a root 2, and also importantly, we see that the magnitude of both components is the same. So that is also an indicator to use the 8-sector circle, because that means we're bisecting a quadrant. So we're bisecting quadrant 4. So I'd be saying to myself, all right, somewhere down there, This terminal point on the complex unit circle is root 2 over 2 minus root 2 over 2I. So we'd be asking ourselves, is there a number I can multiply that terminal point by to get z? And what's that number? What multiplied by root 2 over 2 gives 2 root 2? 4. 4 times that is that. So we have our point down here. This point down here is going to be 4 times out, right? So it's kind of like 1, 2, 3. Maybe I should move it in a little bit. So that's more like 4. So that's 4 times this unit circle point, or number. And if we multiply that out, that's 2 root 2 minus 2 root 2I. Okay, so that means our multiplier is 4, and we can see our angle. We always use an angle between 0 and 2 pi. So our conclusion here is that z is equal to 4 multiplied by CIS 7 pi over 4. That would be our trigonometric form. So the angle is always between 0 and 2 pi, and the coefficient out in front is always a positive number. All right, this one, minus 4 root 3I. What quadrant should we be targeting? Third quadrant? Yeah, both are negative. And do you think we should be going with the steep terminal ray or the less steep terminal ray? Steep. So I hear the steep, and that's because the root 3 is in the second position, right? Down here, the terminal point on the unit circle here, that's minus 1/2 minus root 3 over 2I. So the root 3 is with the second position. That's where it is up here. So yeah, that's where we would, that's what we're thinking. We're thinking, oh, that complex number z is some, hopefully it's a scalar multiple of that terminal point. And sure enough it is. What do we multiply our unit circle point by to get z? Negative 1/2 times what is negative 4? 8. So we're going to multiply that by 8. That's pretty close. So this is going to be 8 multiplied by negative 1/2 minus root 3 over 2I. So that's negative 4 minus 4 root 3I. So that distance is 8. And our conclusion is that z is equal to 8 cosine theta plus I sine theta, where theta is equal to, what's that angle? 4 pi over 3. Exactly. So that's our trigonometric form. How about if we have the complex number negative 6? What is the trigonometric form of that? What's the angle? 180 degrees, pi radians. And what's the r value? Positive 6. Not negative 6. Positive 6. Distance to the origin. So this would be 6 CIS pi. That one's a really easy one to mess up and to put your r value as a negative number. So r is always positive. It's the distance to the point. Positive distance. So the distance to negative 6, you're off on the negative y-axis. The distance to the origin is positive 6. And then the angle is a half a circle rotation. All right. I think I skipped a slide somehow. Did I? Oh, dang it, I moved it. I put it in the wrong place. So that was the one we just did. Oh, we're right there. So this one we just did, so let's move you there. Oh, should be right. Okay. So going the other direction is really straightforward. You just evaluate sine and cosine. So if we have the trigonometric form of a complex number, we just evaluate. Cosine of 120, sine of 120, and we get back to the standard algebraic form. Okay, so now when you're looking at this, what I hope you're seeing is that you have a unit circle number scaled by 6. Over here, unit circle number scaled by 5. So cosine theta plus I sine theta is always right on the unit circle. And then the number out in front tells you how far out or how close in to go from that angle, that point on the terminal, that point on the unit circle. So this is simply 6 times cosine of 120 degrees is negative 1/2. Sine of 120 degrees is root 3 over 2. The I still is there. We distribute the 6. We get negative 3 plus 3 root 3i. So going the other direction is just a matter of evaluating your trig functions, which you guys are all good at. So here we would have 5 times cosine of pi over 3 is positive 1/2. Sine of pi over 3 is root 3 over 2. I carries down. And then we end up with 5 halves plus 5 root 3 over 2 times I. So if you have the trigonometric form, going back to standard form is pretty straightforward. Just evaluate. All right. Why don't we're about to do some operations with complex numbers in trigonometric form. So why don't we take a break right now, and we'll come back in 10 minutes and start up that stuff. All right, so there are 2 operations that we want to look at with this trigonometric form. Some books will call this form of a complex number the polar form. This book calls it the trigonometric form. They talk about polar coordinates in H4, but we're not going to talk about that because you'll do that in Calc 2. But some books will refer to this notation as the polar form and not the trig form. Polar, trig, either one. All right, so here's how we're going to multiply 2 numbers that are in trigonometric form. We are going to, here's what we do. So we have them in polar form or trig form. What we're going to do is take the 2 radii, multiply them together, and then we add the angles. So 2 numbers in trigonometric form, if we want to multiply them, multiply the radii and add the angles. Multiply the radii and add the angles. So for example, see that? A little bigger. So for example, if we have 4 CIS 20 and 2 CIS 30, the way we multiply that together is to multiply the radii and get 8, add the angles and get 50. And then I expanded it from this abbreviated notation, and to get back to standard form, we plug it into the calculator to evaluate. Cosine of 50 degrees times 8, if we round to the nearest, if we round to 2 decimal places, is 5.14. And then sine of 50 times 8 is 6.13 to 2 decimal places, and we still have the I. So multiply the radii, add the angles. Division, very similar. We have them in trigonometric form. We're going to take the radii and divide them. And instead of adding the angles, we subtract them. We take the numerator angle and subtract off the denominator angle. So here's an example. Two numbers in trigonometric form. We divide the coefficients, divide the radii. We get 5. Then we take the numerator angle, subtract off the denominator angle. So 135 minus 45 is 90. And then we evaluate. We don't need a calculator for this. This is a nice angle, 90 degrees. Cosine of 90 is 0. Sine of 90 is 1. And so we end up with our trigonometric form returned to standard form. All right. So here's another one worked out. Let's just go through it. So we're starting out with these two complex numbers in standard form. We want to divide them. In college algebra, you did learn a way to divide complex numbers. Anyone know how you would divide those complex numbers from college algebra, what you did to top and bottom? Did you say conjugate? No? Oh.
I guess that's the answer, right?
Yeah! Multiply by the conjugate. If you multiply top and bottom by the conjugate, you'll be able to get to it. It'll get rid of the I if you multiply by the conjugate. Okay. But we're not going to do that. We're going to do it another way, this long geometric way, or this long trigonometric way. So first we have to convert. If we're trying to do this, if we're trying to convert to trigonometric notation and then multiply or divide, we need to convert 1 minus I into its trigonometric form. So what I said to myself there was that that's going to be on the 8-sector circle. We're bisecting quadrant 4. 1 minus I is down there in quadrant 4, right? The unit circle number, the unit circle terminal point is this. Right? That's on the unit circle right there. And we can see pretty easily if we multiply that unit circle number by root 2, root 2 times root 2 is 2. 2 divided by 2 is 1. So we end up with 1. Root 2 over here multiplied, we end up with minus I. Okay, so that tells us that the R value is root 2 for that number. Now we look at the second complex number down here. 12-sector circle, quadrant 4, come over here. The unit circle number is this, right there. That's on the unit circle, right there. And then we see pretty easily that the multiplier of 2 will eliminate those denominators and get us to the number root 3 minus I. All right, so now we have our trigonometric form for both. This first one, the angle is right here, 7 pi over 4. And for the second one, our angle is right there, 11 pi over 6. So the new rules for division, we divide the radii, divide the two coefficients. And then we do CIS. We take the numerator angle, 7 pi over 4, and subtract off the denominator's angle. We need to get a common denominator. 12 is the common denominator, so I just multiply top and bottom of this by 3, top and bottom of the second one by 2. That gives us that. So there is our trigonometric form of the quotient of those two. Now, depending on what the instructions are, sometimes they're going to want us to just leave it in trigonometric form, and sometimes the point is to go back to other form. So it depends. Now, one other thing I want to say here is that when you're doing trigonometric form, you really don't want to have a negative angle. The trigonometric form, we assume the angle is between 0 and 2 pi. And so right there we have a negative angle. So how would I get the coterminal angle that would be positive? What are we going to add to it? Add 2 pi. Right? We want it to be between 0 and 2 pi, and that's negative. We have to add multiples of 2 pi until we get a number between 0 and 2 pi. Minus pi over 12 is just a little negative. If we add 2 pi to it, we're going to end up with 21 pi over 12. 21 pi over 12. So that would be the answer if we were asked to leave it in trig form. If we were asked to approximate it, we would type into our calculator square root of 2 cosine of 21 pi over 12. Somebody do that. Square root of 2 over 2 multiplied by cosine of 21 pi over 12. Let's round to 2 decimal places. And
23 pi.
23 pi over 12. Yeah. I tried to subtract in my head. Muy mal. All right, 23 pi over 12. Yeah, thank you. Add 1 pi over 12 to that, and we'll get to 2 pi. Right, thank you. So type that in your calculator. Root 2 over 2 cosine 23 pi over 12, and then root 2 over 2 sine 23 pi over 12. Round to 2 decimal places. What do we get for that first one? 0.70. And then minus, we're in quadrant, we know we're in quadrant 4. That angle's in quadrant 4, so I know it's going to be negative point something I to 2 decimal places. Somebody multiplying? Help! I need somebody.
I put it in right. I got 0.07.
0.07? Oh, good. Thank you. Thank you. All right. So there's our standard form approximated to 2 decimal places. So it all kind of depends on what they want for the answer. This is trigonometric form. That's standard form. All right. One more. Let's do a multiplication one now. So here we are squaring 1 minus root 3i. We have 1 minus root 3i multiplied by 1 minus root 3i. So we need to convert that to trigonometric form. So that's jumping out at us, 12-sector circle. And 1 minus root 3i is down here. That's in quadrant 4. 1 minus root 3i. And we have to ask ourselves, what do we multiply this by? This point right here is 1/2 minus root 3 over 2i. What are we going to multiply that by to get 1 minus root 3i? Multiply it by 2. So this distance right here is 2. All right, so this is 2 times the unit circle number. Okay. Now, let's go through the math. So we multiply the radii. 2 times 2 is 4. We add the angles. 5 pi over 3 plus 5 pi over 3 is 10 pi over 3. That number is larger than 2 pi. So what did I do to get to 4 pi over 3? Subtracted 2 pi. If we're going to subtract 2 pi with the denominator of 3, we're subtracting 6 pi over 3. So 10 pi over 3 minus 6 pi over 3 is 4 pi over 3. All right, so if you were asked for the trigonometric form, you'd stop there. If we want to get back to a plus bi form, so standard form, then we evaluate the trig functions. So what we'll do is say that's cosine of 4 pi over 3 plus I sine of 4 pi over 3. Those are nice angles. We know the ratios for those angles. Plug them in, and we get that. So there's our exact form for the multiplication if we're in standard form. All right, so let's just look at that answer for a minute. So that answer, this is the result right there. And we took that number and we squared it and we ended up with that number. So now we're in quadrant 3. And all I want you to sort of think in your mind about, if we jump to degrees for a minute, that angle in degrees is 300 degrees. You agree? And if you take 300 degrees and you double it, you get 600 degrees. And if you subtract off 360 degrees from 600 degrees, you get 240 degrees, which is this angle right here. So this right there, that's 240 degrees to there. All right. So we add the angles when we're multiplying, subtract them when we're dividing. Okay. All right, let's try one from scratch. Are you ready to try one from scratch? Find out. Go ahead and start on number 34. Now these two at least are in trigonometric form already. You don't have to convert. And it says just leave in trigonometric form. So you don't have to convert back. So we'll just do these two in trig form. Multiplication. What do you do with the angles when you're multiplying? Add. Multiply the radii, add the angles. When you're dividing, divide the radii, subtract the angles. Multiply and add, or divide and subtract. If we're just leaving it in trigonometric form, it's actually fairly quick. So what do we do with the 5 and the 2? Multiply to 10. And then, again, the shortcut's really, kind of so convenient. It's hard not to do it. And we add pi over 3 and pi over 4. So we would need a common denominator of 12. So 4 plus 3 is 7. We'll end up with 7 pi over 12. Trigonometric form. And then over here, we're going to do 1/2 divided by 3/8. So that's 1/2 times 8/3 CIS, numerator angle minus denominator angle. So that will be 4/3 CIS. And what did I write there? 2 pi over 2? That should be 2 pi over 3. That's a 3. So 4 pi over 6 minus 1 pi over 6 is 3 pi over 6, which is pi over 2. So there's our trig form for that division. This one would be really easy if the question said go back to standard form. This one would be easy because that's an angle that we can find the ratios for really easily. Cosine of pi over 2, 0, plus I sine of pi over 2. Sine of pi over 2 is 1. So this would end up being 4/3 I if we were asked to go back to standard form. Okay. Any questions on that? That part seems pretty manageable. All right, so let's up the ante. Up the ante. All right. Here's a theorem, really important theorem. It's pronounced demois. Demois. So there's our theorem. So Demois' theorem says that if we take a number in trigonometric form, if we take a complex number in trigonometric form and we raise it to a power, so we're going to raise it to the power of n, that the result is r to the n for the coefficient and n theta for the angle. And that should make perfect sense based on what we just did. If you multiply two complex numbers, you add the angles. So if you multiply a complex number by itself, you're doubling the angle. If you multiply a complex number by itself 3 times, you'd be tripling the angle. And in general, if you multiply a complex number by itself n times, you're going to have to multiply the radius by itself n times, which is r to the n, and you'll be adding the angle to itself n times, which will be n theta. All right. So here's a complex number raised to the 4th power. And according to De Moivre's theorem, we're going to get 2 to the 4th times CIS of 4 times 120 degrees. 2 to the 4th is 16. CIS, 480 degrees. That's not between 0 and 360, so we subtract off 360, we get 120. Okay, so first let's notice this. This is interesting. So we started with this number, 2 CIS 120, which is right there, 2 units from the origin. All right there. And if we raise it to the 4th power, we end up with the same angle. So the result here, this number raised to the 4th power, if we were going to draw the solution, we would go out 16 units along that radial line. So go way out that way 16 times, 16 units. So out there would be 16 CIS of 120. So that's where the 4th power of that complex number is. And it says just leave it in trigonometric notation, so we're good to go. But now this one is pretty easy to convert back if we wanted to. Right? Because cosine of 120, that's a ratio we know. Sine of 120 is a ratio we know, so we could convert back easily. But we won't do it because we don't need to here. All right, next one. Negative root 3 plus I to the 5th. Bless you. So negative root 3 plus I, that's also 2 units from the origin. That's right out here, 2 units from the origin. And we're going to raise it to the 5th power. So this one, we don't have it in trigonometric form, so we need to convert it to trigonometric form before we can raise it to the 5th power. All right. Now in college algebra, you did take these complex numbers and FOIL them. Like here, raised to the 4th power, that would mean you could take the complex number in standard form and multiply it by itself 4 times. That'd be kind of a pain, foiling 4 times. Here you'd be asked to FOIL it 5 times. Right? You could do that. You could do that. But the beauty of De Moivre's theorem is that it allows us to figure out a complex number raised to a very large power pretty easily. So if this was raised to the 15th power, you would never do it by multiplying it all out. But you could do it with De Moivre's theorem pretty easily. All right, so the first step, to implement the theorem, we have to have our complex number in trigonometric form. And so when we look over here, I said, okay, 12-sector circle, probably the less steep terminal ray. The point on the unit circle right there is that. And if we multiply that by positive 2, we've got it. So this is 2 CIS. That angle right there is 150 degrees if we're in degrees. Let's do this one in degrees. 150 degrees. De Moivre's theorem is nice to do in degrees because it's a little easier to multiply it by an integer and then subtract off 360s. It tends to be a little easier than dealing with pi's. All right, so everyone clear on how we got the 2 CIS 150? 2 times the unit circle number is giving us our base here, minus root 3 plus I. Now we raise it to the 5th, so De Moivre's theorem says, oh, raise the radius to the 5th. and multiply the angle by 5. So 2 to the 5th, what's that, 128? 2 times 2 is 4. 4 times 4 is 16. No, 32. 32. 32 CIS. That's going to be 500 plus 250, so 750. Woo, that's too much. That's more than 360. So we subtract off 360 twice, and we get CIS 30. This one, since this one started in standard form, the natural finish point is in standard form. So let's go ahead and put this one back in standard form. So this is 32. We go back to long notation if we need to before we convert. There's the long form. And the cosine of 30 degrees is root 3 over 2. Sine of 30 degrees is 1/2. So our final answer is 16 root 3 plus 16i. So that's where we end up with if we take that complex number and raise it to the 5th power. That's a lot simpler than foiling 5 times. Much simpler. Okay. Any questions on any step? Convert the polar or trigonometric form, and then Demois's theorem. All right, let's do one more. So with Demois's theorem, here's just an outline of the process that we're using, kind of summarizing it. We're going to convert the base to trigonometric form. The way we're typically doing that, if I give you nice numbers, we're going to look at the unit circle in the direction, and then we're going to finish it off by, once we have the trigonometric form, use Demois's theorem, and then convert back to standard form. All right, so let's look at this first one. So we have 5 minus 5 root 3i to the 4th. So let's convert that to trigonometric form. So we're again in quadrant 4. We're suspecting that we're scaling this unit circle number. And sure enough, if you multiply 1/2 by 10, you get 5. So our number is way down there, 10 units from the origin, 5 minus 5 root 3i. Okay. So our trigonometric form then, 10 from the origin, and the unit circle value, 1/2 minus root 3 over 2i, that's at 300 degrees. So right there, 300 degrees. So our trigonometric form, 10 CIS 300. Once we have that trig form, we go to Demois's theorem. We're raising it to the 5th power, the 4th power. Right, 4th? 4th, okay. Raising it to the 4th power. We take the radius, raise it to the 4th power, take the angle, and multiply it by 4. 1200 is obviously more than 360, so we subtract off to get a coterminal angle that's within 0 to 360. So we subtract off 1080, and we get down to that. 10 to the 4th is 10,000. Now, cosine of 120 is minus 1/2. Sine of 120 is root 3 over 2. And then we multiply by I. Distribute the 10,000, and we've now gone back to standard form. So that is the result of 5 minus 5 root 3i to the 4th. All right. So last topic in this section. Let's see see how many slides I have left. I want to. This is a tricky section, but I want you guys to work on one more example before we do roots of a complex number. I want you to do this. So let's suppose we have, three. Yeah, 3 works actually. So, no, not in quadrant 4 again. We've been in quadrant 4 all day. Let's go to quadrant 3. So minus 3i raised to the 6th power. So convert that. So use the Demois's theorem. So convert it to trig form. Use Demois's theorem. Simplify it, and then come back to standard form. Start by converting minus 3i to trigonometric form. Draw a picture, figure out your quadrant, figure out your r value, figure out your theta value. Pretty much all the way through this class, you always have to know r and theta. R and theta. Yeah. Good. Eight-sector circle. Bisecting quadrant 3. Let's find out. All right, here we go. Okay, everyone that I looked at, I think you identified quadrant 3 well. And 8-sector circle, since you're bisecting quadrant 3, the terminal point right there in quadrant 3 is minus root 2 over 2 minus root 2 over 2i. And then we're asking ourselves, what multiplied by that gives negative 3? So it's negative 3 times r equals negative root 2 over 2. Divide both sides by negative 3, so you get root 2 over 6. So that'll be your r value. If I divide it properly. Did anyone else get that r value?
3 root 2.
Oh, maybe I didn't divide properly. Maybe I didn't divide properly. So it's minus 3 times what? Oh, I did the multiplication backwards. Aren't we multiplying by this to get that? Right, we're trying to scale the unit circle value to get the starting value up here. So I should have it reversed. I should have that. I should have it. Let me just rewrite it. So I should have it as minus root 2 over 2 times some number is going to equal the negative 3. Yeah, that's the right direction. So the minuses cancel, and we end up with 6 divided by root 2. And if we rationalize that, we'll get 3 root 2. That's better. Okay, so there's the r value. So our trigonometric form then, let's put you there, minus 3i. So that's equal to r times this unit circle value. Okay, so this all is converted then to 3 root 2 CIS. The angle there is 5 pi over 4. Let's do it in degrees. So that angle is what, 225? And then all that's raised to the 6th power. All right, so 3 root 2 to the 6th power. So 3 root 2 to the 6th power. That means 3 to the 6th power, and then root 2 to the 6th power. Root 2 to the 6th power, that's 2 to the half. 2 to the half to the 6 is 2 to the 3rd. So it's 3 to the 6 times 2 to the 3rd. So it's 3 to the 6 times 2 times 8, whatever that is. All right, so let's write this out. So it's 3 root 2 to the 6th power, and then CIS. And what is our angle when we multiply that out? What do we get? What is 225 multiplied by 6? 1350. All right, so then when we go to simplify this, that's going to be 3 to the 6, and then square root of 2 to the 6. And then what do we get when we reduce that down? 270?
I got 58, 32.
Oh, you got 5832? Yeah?
Isn't it 2 to the 5th?
Wait, where's 2 to the 5th?
No, the multiplication for the 3 square root of 2 to the 6th.
Right here?
Yeah. Or no. Okay, yeah. Sorry. I did it wrong.
Okay, so that looks good there. And then 225 times 6. Are we agreeing on 1350 or not?
I still get 58, 32. Raising 3 to the 6 and then multiplying it by 8.
Oh, okay, that. And what did you get?
58, 32.
5832. Okay, I think two numbers are being spit out because this number over here, 1350 is correct, right? Because that's 1200 plus 150, so that's right. And then when we subtract off, that's the number is not between 0 and 360, so we subtract off 360s, and that number turns into 270. Okay, that looks right. Okay, so, and everybody agrees on 5832? All right, cool. So then we have our 5832, and then what's cosine of 270? 0. And sine of 270? So we end up with that. Move the equal sign over a little bit. So we end up with minus 5832i. That's way down below. We won't draw that, but you can picture it. 5,832 units from the origin straight down. Center of the earth. All right. So now let's do our last crazy topic in this section. Our final craziness. What are the square roots of 1? Pardon? Okay. So the square roots of 1. I hear 1 and negative 1. Yeah? So there and there. How about the fourth roots of 1? Certainly 1 and negative 1, right? Negative 1, quantity to the fourth power is 1, and 1 to the fourth power is 1. Correct? What about I to the fourth? What's I to the fourth? So if you have I to the 1, we call that I squared, we call that negative 1. I cubed, we call that negative I. I to the fourth, 1. So there's the pattern. All right. So I to the fourth is 1. Okay. So that's right there. I to the fourth. What about minus I to the fourth? Minus I to the fourth is the same as I to the fourth, which is 1. 4 solutions evenly spaced. 2 solutions evenly spaced. Anyone want to guess what the 8th roots of 1 would be? Brilliant. Those 8 complex numbers have an 8th power equal to 1. So if you pick any one of these, minus root 2 over 2, minus root 2 over 2i, you raise it to the 8th power, you will get 1. Clearly, these axis points right there, those quadrantal complex numbers, those will all do it. But so will those 4. So do you see the pattern? If you're trying to find the 8th roots of 1, we're going to get 8 answers. So let's convert all 3 of these to equations. So if we want the square roots of 1, we are trying to solve this equation, z squared equals 1. If we're trying to find the 4th roots of 1, we're going to solve this equation, z to the 4th equals 1. And this one is z to the 8th equals 1. So we have to just be able to move from the words to the equation. Does everyone agree that those are the equations that we would be trying to solve? And so what our observation is, when we're trying to find roots of, here we're finding roots of 1. We're going to generalize this to roots of any complex number. But what we're going to see is if we're finding square roots, there's always 2 answers. Cubed roots, 3 answers. 4th roots, 4 answers. 8th roots, 8 answers. Always evenly spaced on a circle. All right. So here is a technique that I suggest for finding the roots of a complex number. Create the equation. Determine the number of solutions and the angle between consecutive solutions. How do we do that? So if we have square roots where there's 2, they're 180 degrees apart. How do we get the 180? Took 360 divided by 2. For looking for 4 solutions, they have to be how far apart? 90. We took 360 divided by 4. If there's 8 solutions, we take 360 divided by 8. They're 45 degrees apart. All right. Then we're going to write the complex number in trigonometric form. And the complex number that I'm talking about is the number we're trying to take the roots of. And then we're going to find subsequent solutions by repeatedly adding the angle from step 3. So if we find one answer, the first answer, and we know that the next answer is 120 degrees apart, we just add 120 degrees. And then add 120 degrees again. That's how we're going to do it. If you look in this book and you want to give yourself heart palpitations, you will look at the formula that is on page 686. and you will give yourself heart palpitations in trying to understand that formula. If you want to do it that way, it's totally fine. I'm going to do it this way, and we'll do several examples, and I think you'll find it a lot easier than trying to understand that formula. The concept here is very simple. The solutions are evenly spaced. If we find one solution, we know them all, because then we just add whatever that space is. All right, so let's go through one. Fourth roots of this complex number. So first, I want the equation. So if I'm trying to find fourth roots, that means I'm trying to solve an equation where I have z to the fourth on the left and the number I'm trying to find the roots of on the right. So now I'm going to say to myself, how many solutions and how far apart? So there's our equation. If it's a fourth power, I know there's 4 solutions, and they have to be 90 degrees apart. Next, we want to convert. We take that side, the right-hand side, and we convert it to trig form. So 4 root 3 minus 4i. Quadrant 4 again. We're living in quadrant 4 today. So it looks like the root 3 is with the first position here. So we're assuming that we're going to stretch that point on the unit circle. Sure enough, if we multiply that by 8, we will get the complex number on the right. So in trigonometric form, we need to know this angle right there. That angle is 330 degrees. So our trigonometric form, 8 CIS 330. All right, so now here's the hard part. Or at least it's not that hard, but it's the subtlest part. So our goal right now is to find one solution. If we find one solution, then we add 90, add 90, add 90. Here's how we find the one solution. This is the trickiest part. So I'm going to call the solutions Z1, Z2, and we're having 4 solutions. Oh, I have them listed sideways. There we go. So I'm going to call the solutions Z1, Z2, Z3, Z4. Because there's 4 numbers that we're looking for. The first solution is found by violating de Moivre's theorem in a way that works. So de Moivre's theorem, remember, said that if you raise to the nth power, you distribute that power to the coefficient and to the angle. Well, it actually does work for rational numbers also. You can use it for this fractional exponent. The way they presented it, they're talking about squaring, cubing, whatever, raising to a positive integer. But if we raise it to this fractional power, what we will do is find one solution. So we're going to take that 1/4 and distribute it to the 8, distribute it to the angle. And when we distribute to the angle, we mean multiply the angle. There's our first solution right there. So we use de Moivre's theorem. So step 4, find the first solution using de Moivre's theorem. So that's the most subtle of all the steps in this process. All right, we've got our first solution. Now we just jump. We know that we add 80, add 90, add 90, and add 90. So 330 divided by 4 is this obscure angle, 82.5. We add 90 to that to get 172.5. We add 90 to that, and we add 90 to that. So there are the 4 answers. And the final step is to convert back to standard form. And we'll round to 2 decimal places. On the test, I'll ask you to round to 2 decimal places so you can get in the habit. And those are our 4 answers. 1, 2, 3, 4. So one thing you want to definitely make sure you can do is test your calculator skills and make sure that when you're plugging in this stuff to your calculator, you're ending up with those answers. Okay? And then Z1, of course, is from up here. That's this one. Okay. And then here I just summarized how you're converting this to trigonometric form. This would be the algebraic way to convert it to trigonometric form. Identify A, identify B, take the square root of the sum of the squares, look at the tangent function, identify your quadrant, and use a reference angle if you need a reference angle. All right, so let's try one. So that's an example. So let's start out with a square root. So step 1, equation. So if we're doing a square root, it's z to the 2. So that's the equation we're trying to solve. Quadratic equation. Z squared equals that. Now we need to convert the right-hand... Oh, no. Now we have to say 2 solutions. How far apart? Yeah, 2 solutions, 180 apart. Exactly. Now we have to convert minus root 3 minus I into trigonometric form. All right, we're in quadrant 3, 12-sector circle. And the root 3 is with the first position, so I'm assuming that we're at the less steep terminal ray, assuming we're right there. The point on the unit circle there is minus root 3 over 2 minus 1/2 I. And we're asking ourselves, is there a scalar that multiplied by the green number gives the purple number? And the answer is 2. Exactly, so let's scale that back to 2. So that is going to be minus root 3 minus I. That's exactly 2 times our unit circle number. Okay, so that angle is 210 degrees. 180 plus 30. So our trigonometric form is going to be 2 CIS 210 degrees. So there is the right-hand side in trig form. Right-hand side in trig form. This we need to go to another page for that. That's too much stuff on that page. Okay. All right. So let's see. And I have another one up there too. That's too many problems on one slide. Let's move this one too to the next page. All right. Get those out of the way. All right. So any questions on that trigonometric form there?
Where did we get the 2?
The 2? No. That 2 came from, we have this complex number. We know it's in quadrant 3. It's floating out here somewhere. We're assuming that it's a multiple of that terminal point on the complex unit circle. And we're asking ourselves, what multiplied by this unit circle number gives us that? And the answer is 2.
Okay.
If we multiply this unit circle number by 2, the denominators disappear and we get the number we're looking for. So that 2 is from the scaling of the unit circle number. All right. Now, the part that's a little tricky, Demois' theorem. So step 4. We know we have 2 solutions, Z1 and Z2. We're going to find our first solution, which we call Z1. So Z1. When we look at our equation, we want to take the square root of that, right? That's our instinct, is to take the square root. So let's do it. So we take our trigonometric form, 2 CIS 210 degrees, and take the square root of it. So that will be our first solution. Our first solution will be whatever that exponent is, the corresponding root. So if that was a 5, we'd have the 5th root up there. If it was a 10, we'd have the 10th root. A 4, we'd have a 4th root. So we're going to take the root of the right-hand side in trig form. And here's where we apply Demois' theorem. Demois' theorem says, okay, distribute that to the coefficient and distribute that to the angle. And by distributing to the angle, we mean multiplication. By distributing to the coefficient out in front, we mean exponent. So we end up with Z1 is root 2 CIS. What's 210 divided by 2? 105, I guess? 105 So there's our first answer. Step 5, we only have one other answer to find. It's root 2 CIS of 285. We add 180 to it. So we get 285 degrees. So here we're adding 180. Add 180. And that's our second solution. Now we are going to plug them into our calculator and present the answers in standard form. So here we'll round to 2 decimal places. So somebody give me an answer for Z1. So it's going to be square root of 2 times cosine of 105. What's square root of 2 times cosine of 105 to 2 decimal places? Say that again?
I got -3.7.
That could be negative 3.7. Cosine is negative.
It's 0.37.
Oh, 0.37. Negative 0.37? You check again, Ashley? Are you in degrees?
Yes, I am.
And then how about sine 105 times root 2? 1.3. You should see, yeah, you should definitely see. And then there's an I. And then Z2 is root 2 times cosine of 285. And then we see that there's always going to be a lot of symmetry. All right. With that, how do you plug it in? So you're in degree mode? So we're going to do square root of 2. Square root of 2. Close it off. Multiply it by cosine of 105 for the first one. And that gives us the minus 0.37.
And what do you do with sine? Okay.
And then, yeah, same thing except you replace the cosine sign. Yep. All right. Let's try another one. Look at those nice answers. Okay. All right, let's... Okay, these ones are actually a little bit easier. The right-hand side here is just -1. That's an easier number to convert to trigonometric form. So there's our first step. We make the equation. How many solutions? 6 solutions. How far apart? 60 degrees apart. All right. Third step. We're going to convert -1 into trigonometric form. That's pretty easy. Do you agree that it's this? So -1 is 1 unit from the origin. So that coefficient's a 1 right there, not a -1. So -1 is 1 unit from the origin, so the R value is +1. And we're over we're over on the negative x-axis, so that's at pi radians or 180 degrees. All right? All right, step 4. We need to find a solution. We find that solution by doing what we want to do. We see a 6th power. We want to take the 6th root to the right side. So do it. We do that. So that's de Moivre's theorem with a fractional exponent. And the coefficient out in front is just a 1. So this is actually just going to simplify to how many degrees? We're going to take the 1/6 and multiply it by 180. So 180 divided by 6, right? So we end up with 30 degrees. So there's our first answer. Now, our second answer. It's in trigonometric form. What do we add to the 30? 60. So we're just going to keep adding 60. So Z3 is going to be CIS of 150. Z4 is going to be CIS of 210. And Z5 will be CIS of 270. And Z6 will be CIS of 330. All right, so those are our 6 answers. And our final step is to convert back. Now, in a case like this, those angles are all multiples of 30, so we can find exact answers. We don't need to type it into the calculator and round to 2 decimal places. So we'll do it exact here. So Z1, cosine of 30 plus I sine of 30. So that's root 3 over 2 plus 1/2 I. Z2, we're at 90 degrees. So 90 degrees, cosine of 90 is 0. Sine of 90 is 1, so that's just I. Z3, we're over at 150. 150 is minus root 3 over 2 plus 1/2 I. Z4, we're at 210. That's minus root 3 over 2 minus 1/2 I. Z5, that's easy. That's minus I. Cosine of 270 is 0. Sine of 270 is minus 1. Multiplied by I. And then our last one is over at 330. So that's root 3 over 2 minus 1/2 I. So those are our 6 answers that have a 6th power equal to -1. And some of your calculators have an I, some don't. You can even type this into your calculator to check. If you put in root 3 over 2 plus 1/2 I and then raise it to the 6th power, you'll get -1. Some calculators have it. Any questions on any of the steps? Let's take a look at this last one up here. Now that we kind of know the process, you can start to do them a little bit quicker, but I mean they're definitely time consuming. So find and graph the 4th roots of I. So we're thinking about our equation as z to the 4th equals I. Z to the 4th equals I. And then we say there's 4 solutions, 90 degrees apart. We have to write the right-hand side in trigonometric form. So we're up here at 90 degrees. And we're on the unit circle because that's only 1 unit from the origin. So this is CIS 90 degrees. Then we find our first solution by doing Demois' theorem with a fractional exponent. He would be proud of us. So then this is CIS. We distribute that 1/4 into the angle. Was that 22.5? Thank you. 22.5 degrees. And then we're going to bootstrap our way through by adding. So CS, we have to add 90 to that, so that's 112.5 degrees, if I added 90 correctly. We're going to add 90 2 more times. So if we add 90 to that 202.5, thank you, and then 292.5. So those would be our 4 answers. And then our final step, I don't have my calculator, so I'm counting on you right now. We got to type these into our calculator and round to 2 decimal places, because those angles are not angles that correspond to ratios that we know. Now, the nice thing is that the radius here is just 1. So we just have to type into our calculator cosine 22.5 and round it to 2 decimal places. 0.92. And then sine of 22.5. 0.38 I. All right, so now that one actually, we could probably use symmetry here because there's only 4. So that's in quadrant 1. And if I want to get 90 degrees away, see if you understand this. So if we're at 0.92 plus 0.38 I, if I want to get 90 degrees away, so right there, if I reverse the coordinates and do 0.38 plus 0.92 I and reverse the first sign, I should be at Z2. So I believe, and double check, type it into your calculator, cosine of 112.5, I think you should get minus 0.38. Double check though. And then if we wanted to get down to this one, that's going to be exactly the reflection of that through the origin. So that's going to be minus 0.92 minus 0.38 I. I'm assuming someone's double checking. You'll yell at me if there's a blunder. And then Z4 would be over here. So that's going to be plus 0.38 minus 0.92 I. So those would be our 4 solutions, back in standard form, rounded to 2 decimal places. Slightly complicated process, but at least it's a process, 6-step process. You know, any of these things that have a process, it just takes a matter of practice, and then you got it. All right, let's take a break. Take a break. See y'all on Tuesday. Have a great weekend.
And we have tutoring tomorrow from 12 to 1.
12 to 1.
In the SOC.
C level, 12 to 1. If you get bored getting tutoring by Jessica, we'll go play ping pong.
It's really fun.
Yes, I can.
Will you sign this too so I can get paid?
Yes,
for
I
one?
can. And today is the 6th. Yes. There you go. You're welcome.
Oh, that's yeah.
I was like,
It's more. I remember being very annoyed.
Gonna make you do 5 of them?
this annoyed feeling in your back. Where you're just like, that's what this gives me.
One of those feelings.
I'm giving
Even
Candy
it's like
one of those
super
feelings also.
It's super easy to get tangled.
What?
It's a tangled web.
I don't think I turned in my time sheet.
Thank you for the help today.
Oh, yeah.
I've got to stop forgetting my calculator.
I looked yesterday at the quiz for 6, and you didn't see open it up.
Oh, I didn't?
No,
Oh, I'm sorry. Oh.
it's okay.
All right, yeah, I will go do that right now.
Cool, thank you.
And now, you had also emailed me about, there was one answer there that you had a sign error on.
Yeah, that might,
Everything is on
Because you were finding the tangent value,
yeah.
and you put that as a positive with a negative.
No, I put that it was negative in my math lab, thought it was positive.
Oh, that's what it was. That's what it was.
Yeah.
Okay, yeah.
So it's just a little error, it's just like the one little thing I got wrong.
Yeah. I will, and that's on, okay, yeah, I know which quiz it's on. Yep. I will go do that right now.
Thank you.
Assuming I don't get intercepted on the way to my office.
I was just wondering, so we're trying to find Z like to the 6th power.
Yeah.
Is it ever going to be an odd number?
Yeah.
Oh yeah.
You-
Did we do that at the beginning or what?
I never even thought about that.
Because I'm like, it's easy to go, oh yeah, well,
Yeah,
do we have to use the other equation to figure out an odd number?
no, we'll still use the same thing. We'll do it the same way. Yeah, I guess we did mostly evens. They're all evens.
Because it's
That's
easy.
That's a coincidence. It's
Oh,
just
okay.
it's the same difficulty.
I was just like, well, because if you go 4, you get, oh, that's 90 degrees, you know.
So if it's 3, it's 120 degrees.
Okay.
So if it's 3, it's 120 degrees, and if it's 5, it's 360 divided by 5.
Oh, so you do, okay, that's all you do.
Yeah,
Oh,
that's all
okay,
you do,
okay.
which is 72. Which is 72.
Okay.
If it's 5, yeah. It'll work the same way.
All right.
Yeah. No, that's a good question. That's a good observation that we did all evens. So that's a natural question.
Oh, this makes so much sense.